12.1 is going to talk about sequences and introduce a lot of notation. So sequences are best introduced with a famous example that goes back to the 1300s, a guy by the name of Fibonacci. The funny thing about his name, Fibonacci, is that one translation of it is blockhead. But he's anything but a blockhead. He was actually a really, really smart guy. And in his book, he considered the following problems about the number of breeding pairs of rabbits. So after 1 month, pair has, some offspring, and then after another month, they can start breeding, etc. So the number of breeding pairs you have increases like this. 1 and 1 gives you 2. 1 and 2 gives you 3. 2 and 3 gives you 5. What would be the next term in this sequence? It'd be 8, and then 13, 21, etc. And this is what's called the Fibonacci sequence. It's a very famous sequence. He talked about his book, Liber Abaci, in which he also introduced the Western civilization to a different number system. Fibonacci numbers come up all over the place in a lot of crazy places. So there's a picture of Fibonacci. I'm going to skip through a lot of this stuff, but here's some of the places you'll see Fibonacci numbers in nature. In the spirals, if you count I think they're called bracteoles of a pine cone, pineapple, Pascal's triangle, we'll go over that. But even in modern day, they use it, a Fibonacci retracement in investing. You can graph the Fibonacci sequence, and if I connect this with a spiral, you get, you get, what's it called, the golden spiral. The golden ratio is related to the golden spiral through this. The golden ratio would be the ratio of one side of this rectangle to another. And these are just all over the place. You see them in spiral galaxies. It was mentioned in the Da Vinci Code. The path that a hawk will take, spiraling around looking for its prey, is also going to be a golden spiral. What's that? What does it mean? That's another class. We'll talk about that. So for now, let's work with sequences, and you're going to run out of letters, or you're going to run out of things. If we do 1, 1, 2, 3, 5, 8, 13, 21, etc. When you're working with these things, you kind of run out of letters if you try to give each one a different letter. So what we do when we're working with a sequence is we give it a name and then we subscript it. So this would be A sub 1, then A sub 2, A sub 3, A sub 4, A sub 5, etc. And if you want, the 5th term of the sequence, there it is. 6th term, etc. So this notation refers to an element in a sequence. Now, a lot of times they're going to give you the actual formula for that term in a sequence. For example, problem number 6. They tell you A sub n is n squared minus 1. And they ask you for the first 4 terms and the 100th term in this sequence. Okay, so the first term would be A sub 1 is going to be 1 squared minus 1. So A sub 1 is 0. A sub 2 would be 3. A sub 3 would be what? 8. And A sub 4 would be 15. The last one they wanted was A sub 100. So the nice thing here is that I don't have to get all the terms in between. I can just jump up to 100. A sub 100 is going to be 9,999. Okay, so what am I trying to get across here? I'm just trying to show you some notation. And that notation is going to be important when we start writing things and rewriting things. We're going to continue to work with sequences of different types, geometric sequences, arithmetic sequences. But let's do one more thing here. Problem number 12 kind of similar to problem number 6. This time, there's this crazy term of -1 to the n plus 1 out in front. And let's figure out what happens with that. So we'll start by putting in a 1 here to figure out a sub 1. So that would give me -1 to the 1 plus 1 times 1 over 1 plus 1. Now -1 to the 2 power is what? It's 1. So I get a half. Let's try -1 to the 2 plus 1 power. 2 plus 1. This time it's going to simplify to -1 to the 3rd power times 2/3. -2/3. And we got a couple more to do. A sub 3 would be -1 to the 3 plus 1 power. 3 plus 1. Can you see the effect of the negative out in front here? What's it making the sequence do? Well, maybe one more term will help us decide. So that's a sub 3. A sub 4. Why don't you calculate a sub 4? See what you can come up with. Anmar, what'd you get? Okay. Good. So -1 to an odd power is negative, so I get -4 over 5. Let me ask my question again. What's that -1 term out in front doing to the sequence? What's its overall effect? Perfect. So basically what's happening is it makes the sequence alternate in sign. One of them's positive, the next one's negative, positive, negative, positive, negative, etc. Last but not least, we can do a sub 100, which would be -1 to the 100 plus 1, 100 over 100 plus 1. That's going to be, well, you tell me, is this going to be positive or negative here for a sub 100? Negative 100 over 101. And the trick there is that, well, we have an odd exponent. So in this example, you were actually given the formula and we wrote out a few terms. In the next example, we're going to do kind of the reverse. We're going to start out with a few terms and try and figure out the formula. We'll start with problem number 28. So my terms are 1, 3, 5, and 7. So this is a sub 1, a sub 2, a sub 3, a sub 4. What I want to figure out is what do these things look like in general? That is a sub n. Okay, well, well, there's really a couple ways you could do this. If you wanted to do it in what's called a recursive fashion, you could do it that way. But let's see here. Well, if I start out with a sub 1, to get to the next one, I'm adding 2. Yeah, and then I add 2 again. Well, let me see if I can't think of this a different way. A sub 1 is 1. A sub 2 is 1 plus 2. A sub 3 is 1 plus 2 plus 2 again. A sub 4 is 1 plus 2 plus 2 plus 2. And what I'm getting at here is this. I've got a sub 4 is 1 plus 3 times 2. A sub 3 is 1 plus 2 times 2. A sub 2 is 1 plus 1 times 2. So they all have something in common here. They all have a 2 here. I'm not going to worry about the first one. Although actually you could fit the first one into this pattern, right? What would it be? 0 times 2. So all of them fit in this pattern. Let's see if we can't figure out what the general term is then. A sub n. What's a sub n? Well, 1. Now let's take a look at these here. A 4 here goes with a 3 here. A 3 here goes with a 2 here. There you go. So a 2 and a 1. This is 1 less than this. 3 minus 1 is 2. 4 minus 1 is 3. So in general, what you're going to have is 1 plus n minus 1 times 2. That's the general term in this sequence. So this is the formula that you're looking for. And you can verify it. You can check it out with, I mean, for instance, what would the next term be right here? What would a sub 5 be? Right here. Anyone for a sub 5? It'd be 9, right? If I did a sub 5 with this formula, does it work? A sub 5 would be 1 plus 5 minus 1 times 2. So 1 plus 4 times 2 is 9. It checks. Let's try a little bit of a different one. Problem number 34. 0.3, 0.0, excuse me, 0.03, 0.003. Not quite. Let me rewrite these a little bit more. 3 over 10, 3 over 100, 3 over 1,000. What do you suppose the next term is going to be? Yeah, 3 over 10,000. And now let's put some numbers to these. This is a sub 1, a sub 2, a sub 3, a sub 4, a sub 5. And again, you might help yourself by thinking of this not as just a 10, but these are powers of 10, right? 10 to the first, 10 to the second, 10 to the third, 10 to the fourth, etc.
So it's x, I'm sorry, 3.
So the general form a sub n has to be 3 over something. I mean, they all have the 3 in common, so let's put the 3 in the numerator. How about in the denominator? What am I going to put in the denominator? Well, some power of 10, right? But here's where you want to start lining things up in the denominator. A sub 2, exponents 1. A sub 3, exponents 2. A sub 4, exponents 3. And so on. So what seems to be the pattern in going from a sub 2 to this, or a sub 3 to this? It'd be n minus 1 again. So that's your general term, is 3 over 10 to the n minus 1. Does it work for the first term? Does it work for a sub 1? 10 to the 0 power is 1. So it works. I'm going to introduce to you some new notation. Stuff that maybe if you're looking at an old exam carefully and you're wondering, like, what's that symbol up on top? What's that all about? Maybe you'll see it. And it's called sigma notation. Sigma. Yeah, sigma is going to be used for sum. So it's a Greek word. This is the capital letter sigma. You'll see a lot of fraternities on campus. Campuses all over the place. Sigma Chi, Sigma Delta, whatever. That's capital sigma. Lowercase sigma looks like that. Not that we need that. Let's take a look at what this sigma notation is, though. And I'm going to do it by example. Problem number 48 gives us the sum from k equals 1 to 4 of k squared. If you've ever done any computer programming, had to run some loops, this is going to look a little bit familiar. What this means is we're going to start out at k equal 1 and plug in a 1 into this expression. So I'll get 1 squared plus, let's move on to the next one, k equal 2. So that'd be a 2 squared. K equal 3. How far do you think I'm going to play this game? All the way up to 4. So the top number here is the upper limit on your summation. Okay. So let's see, what are we going to get? Let's see, it's going to be 16, and 9 is 25, and 5, 30. We get 30. Jeff, in charge of checking me on that one. Ah, dropped the ball. 30? All right, good. Let's try a different one. We'll try a couple more here. Problem number 54. Now, what's true about these kinds of summations is it doesn't really matter what letter you use. Typically, I, J, and K seem to be favorites amongst mathematicians for this stuff, but you can use any letter that you want. In problem 54, we got the sum from I equals 1 to 3 of I times 2 to the I. So kind of like what we did for problem number 48, one at a time you have to put in these numbers. So at I equal 1, you're going to have 1 times 2 to the first power, and then 2 times 2 to the second power, and then 3 times 2 to the third power. So what, 33? 34? Yes, 34, thank you. Now, my goal here is not necessarily to make you, do a lot of tedious arithmetic. What we're working on is trying to understand this notation. We're going to do a couple more examples. Problem 52. The sum from I equals 4 to 12 of 10. Now this one's got a little bit of a trick in it, a little nuance that you need to pick up. But as far as writing out what this means, this is called expanding the sum here. So if you were to expand this sum, it'd be 10 plus 10 plus 10. Here's the important question. How many 10s will I be adding up? But we're starting at 4 though, right? So there's nothing to plug in for I. So we have I equal 4, I equal 5, I equal 6, 7. Now let's just keep going. I equal 8, I equal 9, I equal 10, 11, and 12. Good. If you count them, there's actually 9 of these terms. So 9 times 10 would be 90. Now, realistically, if you're doing a problem like this, you wouldn't really just do this, right? You would just take the number of terms times this number. So how are you going to tell how many terms there are in a sequence like, or a series like this? What's the shortcut? But where's the 3 coming from? There's a 4 here. All right, so what I would suggest is 12 minus 4 plus 1, or top minus bottom plus 1 is the number of terms. Now, if your sequence is starting at 1, then great. It's just whatever it looks like. In the first 2 examples, we had 4 and 3 respectively. But if it's starting at something other than 1, then you want to keep this part in mind.
Are we always to just assume that it's only whole numbers? We wouldn't be using.
Yes. Yeah. This kind of work only applies to whole numbers. So you can't have, 4.3 or 6.9 in there or something like that. So yeah, it only applies to whole numbers. So here's one with a little historical basis. I think I mentioned this before. Let's see, k equals 1 to 100 of k. I talked about Gauss before, right? No. Yeah, I think I did. Maybe it was in 1150 class. I don't know. Olivia, did I talk about Gauss? Yeah, okay. So this is when his teacher got mad at the class, told him to add up the first 100 numbers. This is a very compact form of asking somebody to add up the first 100 numbers. 1 plus 2 plus 3 plus 4, all the way up to 99 and 100. So, and the sum for that was 5,050. There's actually some formulas that you learn that'll help you calculate that almost as fast as Gauss did. So let's try problem 68. 2 plus 5 plus 8 plus all the way up to 29. What if I wanted to write that with a summation? Well, I could. This is a sub 1, a sub 2, a sub 3. The question is, what's that? A sub what? Well, I don't know. It would help if we had the general term in this one. It's going to have to be a little bit more plus than plus 3. What you're going to see, and we'll get more practice on this when we start covering 12.1, 12.2, and 12.3, is that this is an arithmetic sequence. You can rewrite this as a sub n equals 2, your first term, plus n minus 1 times this common difference. What am I adding to get from one term to the next? 3. So there, yeah. And we'll see this next time. Your general term sequences is going to be a sub n is going to be a sub 1 plus n minus 1 times d. So I'm not really spilling any secrets. We'll see that soon. If that's the case, what number would give me 29? How many terms do I have to go out? Well, let's solve for n in this equation. That would mean I have to subtract 2. 27 equals n minus 1 times 3. Divide by 3. Perfect step here. 3 into 27 is 9. 9 minus 1 add 1 to both sides, you get n equals 10. Now, could you have got that just by kind of working your way out here and counting? Sure, absolutely. But you might not always be quite that lucky. If I'm going to write this now using summation notation, it would be the sum from I equals 1 to 10 of this expression. 2 plus I minus 1 times 3. Let's do one that's a little bit easier because it doesn't require us to do any fancy footwork like this. And that'd be problem number 70. This one's definitely a lot harder than the next one. So this is a good one to finish up with. Problem number 70 gives you this sequence, actually I should say this series, 1 over 2 ln of 2 minus 1 over 3 ln of 3 plus 1 over 4 ln of 4, and so on. All the way down to 1 over 100 ln of 100. We want to write this with summation notation. What do you think the general term is going to look like for this? Well, it has to have a fraction, right? A 1 over something. Good, that's even closer. And then what? All right, we're going to have to deal with that negative 1. These are going to alternate, so I'll deal with that in a minute. But how about the denominator term? I'm going to have an ln of something, right? What variable do you want to use for our index? You want to use n or I or k? K. All right, k it is. So we'll use k. Where do you think we're going to start with our summation? 2 up to 100. I need an expression for that term in the denominator. What do these things look like in general? All right, they're going to alternate, so we're going to need negative 1 to some power. You know, the k power. Let's see if that works. But something times log, and then log of what? Just k, right? 2 and 2, 3 and 3, 4 and 4, k and k. From 2 to 100. Does this alternate in the right way, or do I need negative 1 to the k plus 1? Well, if I put in a 2 here, negative 1 squared is going to be positive or negative? Positive. If I put in a 3 here, negative. 4, positive. So it alternates in the right way. We're done. All set with 70. We'll practice some more of this next week. For homework, try 3 through 11, 21, 23, 27 through 33, 39 through 43, and 47 through 71. See ya!